speaker comes to us. She is the Vice President and Global CTO for Sales at Dell, which is a Cube Global founding partner. Please give it up for Patricia Florissi.
Good afternoon, everyone. It's a pleasure to be here today. And we are going to be talking a little bit about how technology is changing the way we work, live, and think in an ever-increasing pace. And one of the reasons why this is happening is because the incremental cost or the marginal cost of actually adding intelligence, communication, sensor awareness, making our objects animated is actually approaching zero. What does that mean? It means that for a company that makes an umbrella, to make that umbrella your umbrella, it's almost zero in terms of additional cost. And why do you care to have your personalized umbrella versus a common umbrella? Because when you wake up, your umbrella wakes up with you. Your umbrella is connected to your smartphone. It knows when the alarm went off. It connects to your calendar. It knows where you're going to be the whole day. It connects to internet websites and finds out what's the weather like on every single place that you're going to go. And it then finds out if the umbrella needs to go with you or not. Now, if the umbrella makes an executive decision that should go with you, the umbrella will have what is called a digital tantrum. It will vibrate, it will blink, it will send you a text, it will send you a WhatsApp, it will send you an email, a Facebook message, whatever is necessary to call your attention. And if you decide that even so you're not taking the umbrella with you, the umbrella will let the insurance company know, because should you fall sick, you should not be entitled to a reimbursement of the costs of your disease. Now, this is happening because today technology is advancing at a constant speed of 10 times every 5 years. According to Moore's law, the performance increases or doubles every 18 months. And if you actually compound that, it increases 10 times every 5 years. But this is only a constant exponent. What if it's actually moving faster? I'll give you a concrete example. In 1989, the US government decided that it should have the sequence of at least one DNA. As you know, a DNA has about 6.4 billion letters, so it actually created one of the largest science collaboration projects in history. It actually assembled hundreds of universities, and each university assembled researchers and students, and it split a genome into pieces and gave one piece to each institution to actually sequence the portion of the DNA that they had. This is one very successful project because it ended ahead of time and it cost much less than originally budgeted. It was supposed to take 15 years. It ended on 13. And it was supposed to cost $3 billion, and it cost only 2.7. And you ask yourself why. Well, it has been said that robots are not replacing humans. Instead, humans have been filling in for robots until they became viable, which is a whole new way of looking at. And it was the same way that actually a group of students in 3 different places in the world actually started creating the sequence machine. They said, why should humans do the repetitive task of sequencing the DNA manually? Why can't I have a device where I put a wet sample of blood, a sample of blood or spit from your saliva, and actually I'll create the 6.4 billion letters on the other hand? And so they did. So in 2001, 11 years into the scientific collaboration where humans were manually sequencing the DNA, the sequencing machine could already sequence one DNA for $100 million. And if it had followed Moore's law, it would cost today about $1 million to sequence a single DNA. But it went faster, so much faster that today it only costs about $1,000. Why do we care? because if it actually continues at that projection, in 2031, it will only cost $1 to sequence a DNA. So when we actually think about science and what is possible today, we shouldn't project for how much it costs today, but how much it will cost in the near future. So when we started talking about big data a couple of years ago, I actually ended every presentation that I had with think big, think data, think big data. And I actually realized that I was wrong. Why? Because when you have a constant exponent of 10 times every 5 years, but in many areas you are going faster, much faster, you actually have to think bigger. You can no longer think big data because it's not enough. You have to go faster, and you have to identify major trends that are happening in the industry, and you have to think bigger. You have to think data still, but you have to think bigger data. And this is what we are here to talk about, this new concept of bigger data. If I am a historian, in 10 years from now, I'm going to say, and at the beginning of data science, there was one lake. And that's how everything started. We occupied ourselves with saying, how am I going to ingest that data? Is it structured, unstructured, batch, real-time, streaming? But we thought and we lived under the impression that one data lake was enough. Is it? I don't think so. Because we have the perfect storm that is preventing data from moving. Number one, you have IoT. You have the fact that we are collecting huge amounts of data at the edge, and it is impossible to actually bring all of that data to a central location. Number two, you have the fact that you have regulatory compliance that is preventing data moving across social, political, and economical boundaries. Three, you have the fact that you have bandwidth constraints, especially when you have IoT, that the sensors are being put in places that is hard for humans to reach, and therefore has constraints on the network as well. And even when you have high bandwidth, the amount of data that we want to transport far exceeds our capability of financing it. And furthermore, you have the issue of multi-cloud. You have data on all kinds of clouds. You have ERP data on VersaStream, SAP. You have customer relationship management on Salesforce. And you have human resources on Workday, and so on and so forth. And last but not least, you have all the data that you collected before that we call heritage data, antique data, that resides in pockets, and it is hard to take out. So when you have to think about bigger data, we have to think about two aspects. Number one, data is going to be distributed. There won't be one lake, but multi-lakes. And number two, you have to think at worldwide scale. If we were to take an X-ray of actually how the anatomy of data across the world looks like, you would find the spots of data, what we call data zones, that are scattered everywhere. And what we want to provide, and what we are working and doing research on, is how to provide a view of the data that looks like a data fabric, all connected, all can be analyzed in place, even though the data is not moving. I want to actually explain how we apply that concept in the case of bioinformatics. So let me switch a little bit about why we can't have one lake anymore, why do we need multi-lake, to explain a real-world example of why and where that is absolutely the case, and we need to think different. When you have infectious diseases, they still take millions or billions of lives, and they cost billions of dollars every year. And what is different? Well, these infectious diseases are caused by pathogen. It can be a fungi, a bacteria, a virus, but this is a pathogen in your organism that actually installs itself, and you no longer, it causes diseases. It used to be the case that a pathogen was actually a combination of genes on your genome that made the microorganism disease-causing. And what is happening recently is that even though a microorganism may not have the combination of genes, that microorganism may be horizontally transferring one gene to another microorganism, and now that the other microorganism, the receiving end, has a combination of genes that is disease-causing. So when the gene was in the original microorganism, you didn't have a problem. When the gene horizontally transferred to a host, the host now can cause a disease because of the new combination of genes that resides there. And why do we have today more horizontal gene transfers than we had in the past? For one simple reason. You have global warming, which is causing massive migrations of disease vectors from one end to another. And you have another issue also, is the fact that because of social and political unrest, you actually have migration of people that actually are outside of their environment in contact with other disease vectors in areas with poor sanitation. This concentration has caused massive amounts of horizontal transfer diseases. And if you actually look at the director of vaccines from GSK, he says the way that we are doing today disease prevention is by basically allowing an epidemic to emerge and then react to the epidemic itself. And it is like inventing and buying car insurance after the accident actually happens. And we need to understand the genome composition of those pathogens in order to come up with the right medication. So if you actually look today at a microbiome like a sample of water is a collection of microorganisms. So if you believe that people are getting contaminated by water, you actually take a sample of water and you analyze that sample by isolating a bacteria, isolating a pathogen, and looking for the genome composition of that pathogen. How you do that? You put it in a petri dish, you try to kill all the other bacteria, leave just one, and then you sequence that particular bacteria or fungi and virus. And why do we go through the process of doing an isolation? Well, we go through that because it costs a lot of money to actually sequence a DNA. So you have to actually sequence, isolate one, and sequence just one. But sequencing, isolating one, is a process that interferes with the environment itself. By isolating that pathogen, you are killing others, and the pathogen that actually survives may have mutated in order to survive the process, and not all pathogens can be isolated. So the other big problem is that when you isolate one pathogen, you are only looking for combination of genes in a single microorganism. And what if what is causing water to be contaminated is the fact that it has several pathogens with several combinations of genes that, even though they have not been horizontally transferred to a single pathogen, the combination of those genes is causing the disease. And I would like you to please pay attention to this slide, because that's where the power of bigger data comes along. The power of bigger data is based on the fact that if I could sequence all of the genomes, all of the bacteria, all of the fungi, all of the virus within a microbiome, within a sample of contaminated water, if I could just do that, I could look for patterns of genes that are present across the microbiome, across the pathogens that causes the disease. And that would advance science a whole lot. So what we have done is that while this process is based on the assumption that it costs a lot to sequence, and therefore I have to isolate one pathogen and sequence just one, we actually are working on the assumption that Today it costs $1,000, but soon it's going to cost $1. And if it costs $1, I no longer need to isolate, and I can do a whole microbiome analysis. I can take the sample, and I can sequence all of the pathogens, all of the microorganisms, and then I can do the following. I can treat them as if they were part of a bigger set, and I can use bigger data analytics to find any combination of genes regardless of where they reside. And this is rather powerful. So we created a simulation where we assume that number one, you can actually sequence the entire microbiome, but number two, you can do that at worldwide scale. We imagine a world where you have sequencing centers scattered all over at worldwide distributed level, globally. Each sequencing center is sequencing close to the source of disease, the entire microbiome. We can then apply bigger data analytics to each sequencing center in place to identify for patterns, and then we share those patterns we actually use locally by clustering algorithms to tie combination of genes, completely exploratory, combination of genes with people or animals or humans that actually have a similar pattern of symptoms, and then we can identify diseases before they become an epidemic. And we have done that at worldwide scale. So now let me tell you the technology that we use to distribute and automate computation. We believe that our vision of the world at Dell Technologies is the fact that at the physical layer, at the bottom layer, you have data zones. A data zone is any place in the world where you have data and processing power. And it can be as small as a sensor, as a vibration sensor. It can be as big as an instance of a cloud. It can be an IoT gateway. That's what we call a data zone. And even though at the physical layer, those data zones are scattered, at the logical layer, you can imagine that they actually form a virtual computing cluster. And that's the thought we would like to leave you with. We believe in a world where a data scientist will come, and let's say, for example, you have buildings, you have hospitals, you have sequencing centers. They are sending data to a data zone. It can be a cloud near the collection point. And a data scientist will come in, connect to the virtual computing cluster, and say, I want to do a worldwide scale computation across all the genomic files of all the environments that have a particular set of symptoms. Or I can do completely exploratory big data analysis. The framework we have created allows the virtual computing node where the computation starts to actually distribute across all the other virtual computing nodes in the cluster. Each one of those virtual computing nodes push analytics to where the data is, very much inspired on the original design of the distributed file system and distributed computing in Google, but done at worldwide scale. Then at each location we do analytics, and when the results are actually obtained, the local results, we then share those local results back, and they make themselves back to the data scientist where a global computation is done and the final result is presented. But all of that happens in the background. The data scientist doesn't need to know where the data is located. What are the names of the individual files? What are the individual paths of the file? The data scientist can treat data at the metadata level, and the distributed computing pushes computation to where the data source is. And the computing framework is the same, regardless if you have a cloud, an IoT gateway, an embedded computing, a sensor, or anything as a destination. This is what we call WWH, the worldwide herd, and it is completely based on this notion of metadata and of meta-resource. The data scientist operates at the level of a meta-resource, which is an abstraction that is tagged with metadata tag, and where data engineers actually map the meta-resource to a physical location at each one of the data zones. We believe that the world is going to have 3 layers. The physical layer, the data zone layer that exists today, and it is only going to expand. You have the metadata fabric that abstracts the physical world into meta-resources. And you are going to have the analytics fabric, where data scientists should operate and be completely hidden from the physical location of the data itself. I'm almost running out of time. I would like to leave you with one message today. In life, there are 3 types of people. People that make it happen, people that watch it happen, and people that do not know what happened. We are in the midst of the dawn of a new era. It's the digital era. And each one of us will have to think very carefully what type of person we want to be. Technology is a team sport, because together we are better. Only together we can accomplish things that no one else can. We believe that the time is now to change the world, one change at a time. Let your transformation begin. Thank you very, very much.
Thank you very much, Patricia, for your insights from Dell. We appreciate it.
Thank you.
Hope to see you soon. If you have a question for Patricia, I encourage you to approach her on the sidelines of the CUBE conference. Will you be hanging around a little bit today?
Yes, absolutely.
Great. Okay, so please approach Patricia on the sidelines with all your questions. Thank you so much.